before going to my actual talk, I wanted to say at least a bit about my background and my motivations for doing what I'm doing, just to kind of give you an idea, you know, how I got to the question of this talk. So I have a background in art history and in philosophy. And when I was a philosophy student, I focused on the work of Martin Heidegger, a bit of a famous but also obscure philosopher, if you want. And more specifically, I focused on his essay on technique. Die Frage nach der Technik. This essay is mostly interpreted in a very pessimistic and it's read like pessimistically, the way he writes. It's about a techno-science where everybody is basically going wrong. So I read it quite differently. So, and the way I read it has to do with the main quote in the essay, which is a quote by Hölderlin. Wo aber Gefahr ist, wächst das rettende Auge. So where there is danger. So I'm not going to do a lot of metaphysics. This is just to, where there is danger, there is also the saving power. And for me, that was kind of an appeal to basically jump right into the technology, into the technique, and rather than kind of starting to destroy my computer because I really had issues with the machine, I wanted to understand them. And so that's how I got basically to the history of computing, because this was my way into the field, if you want. So I became, and I'm still quite convinced that doing history of computing, doing history of programming, engaging with the original sources is one way, not the only way, to kind of understand better how we arrived here today, and maybe where we might want to go. So this is it. So I recently also became the PI of the Programmi research project, which basically has the title of this talk as a title for the project. So we have quite a diverse group of people with very different backgrounds, and so this is quite challenging because, you know, we have to pull ourselves, everybody in the group has to pull him or herself out of their comfort zones. I specifically wanted to mention Thomas Petlicek because the second part of this talk is very much based on a collaboration we have within the project. Okay, so what is a computer program and why should you care about this question? Obviously, there are a lot of kind of basic, clear definitions around. So this is just a random definition I picked from the web. A computer program is a collection of instructions that performs a specific task when executed by a computer. Most computer devices require programs to function properly. A computer program is usually written by a computer programmer in programming languages. But of course, these kind of definitions do not necessarily help when confronted with a very broad range of basic issues with which we are faced today. Indeed, how would that definition help us when trying to understand why some program has decided that your subsistence ratios have been stopped because it cannot recognize you as a citizen? So I know that a lot of people are working on a lot of these issues specifically. I'm not doing that. My approach, as I kind of already explained at the start of the talk, is very indirect and very historical. Okay, so more specifically, my approach would be, we could call my approach integrated history and philosophy. So what I would like to do here is to, because I decided, when I accepted to give this talk, initially I wanted to like a pure historical talk, but then I decided I will do a kind of general talk. So I'm doing a general talk. So what I will try to do, my talk is basically in two parts. So the first part, the flash or from history, basically what I want to do there is to kind of derive a number of basic insights I got from the history of computing by discussing a couple of cases. And then based on these cases, based on these insights, I hope they are not too trivial for you, based on these insights, I want to derive a kind of philosophical framework which is very much about the idea of epistemological obstacles, and which is a concept from Gaston Bachelard, a philosopher of science. And then I will move on to a proposal and a discussion. So lessons from history or not. So the first insight has to do with words, and I was very happy to find this quote by Perlis on the cool Mesh website. A language that doesn't affect the way you think about programming is not worth knowing. Well, this is true in general about language, right? So if you use a specific word, this really impacts your thinking. And so it's quite important to be aware of the semantic connotations of that word. Now, in history, you have people like Karin Shemla. She's a rather well-known historian of mathematics. She has been working exactly on this methodologically wise. So she remarks in one of her papers, historians often worked under the assumption that the main components of scientific text problems, algorithms, and so on, are essentially ahistorical objects which can be approached as some present-day counterparts. So this is a mistake philosophers definitely, but also historians make. They make an assumption about, they assume that certain concepts do not have a history, and because of that, you kind of are confronted with blind spots. There are blind spots in the way you perceive of history. So words carry a semantical history, and words are historical. They develop, they don't have a stable meaning. So here is, I'll discuss two cases. So the first case is the case of, so these are very quick, short cases, right? So the first case is a case of algorithms. So as most of you probably know, the origins of the word algorithm go back to Al-Khwarizmi's Hindu art of reckoning. So this manuscript, which is lost, so we only have Latin translations of that, is introduces basically the decimal notation and then also some arithmetical procedures to work in the notation. But the way it was referred to when his name became the word algorithm, it was not about the procedures, it was about the notation. So algorithm in its initial usage had nothing, well, it was more about the notation than about procedures. Clearly, by the 1960s and the 1970s, the notion of algorithm had changed. It was in that new meaning that it was instrumentalized by, amongst others, Knut, but also by the algo community and the ACM community in general, to give the new computing field academic seriousness by framing it as a mathematical field. So, you know, basically the interpretation there is algorithm is a step-by-step procedure, it's a recipe. So what about today? So this is a hypothesis, so please, it's a research I'm about to start, so it's very hypothetical. So what about today? So my impression at least is that the semantics of algorithm is changing again, especially in popular discourse, where algorithm is used, for instance, Facebook algorithm, algorithmic bias, as if a mathematical algorithm can have a bias. Recently, a paper in the Guardian, how algorithms punish the poor. So algorithm is becoming, is undergoing a kind of, Fabio Fossa, I saw a great talk by him about robotics and AI and how you have there, you can speak there also about the process of semantic extension. So the notion of algorithm underwent a semantic extension. It was extended to software and to systems and programs, but that doesn't mean that it's stripped of its past, so it still bears the mathematical connotations. And because of that, this can be quite dangerous, and to some, it can result in a quite dangerous and to some a useful illusion of a world governed not by human-made and complex software, but by mathematics. So this is the thing about the algorithms. The second case has to do with a narrative, the art to science narrative in the history of programming. So it comes down to the rather common idea that programming has developed from an art in the 1950s to a science in the late 1960s and 70s, a process which was supposedly sped up by the so-called software crisis. So I fear I do not have time to go through much details here, but the bottom line is that such narratives assign quite reductive and one-dimensional meanings to the word art and science. Moreover, they make a value judgment about art being less good than science, and thus also about, I don't know, my text is somehow, I shouldn't read, that's why I don't like to read text because they always confuse me. So, so they make a value judgment about art being less good than science, and thus also about history of technology, having the purpose to always improve on itself, being held by history, by theory. So basically, what I was writing here, it's if you take this narrative very seriously by assuming that an artistic practice is bad and a scientific practice is good, you're kind of imposing a telos on the history of technology, which is something I at least am not buying. I don't believe in a history with telos. So yeah, I'm not going to read the quotes. So this kind of opposition between art and science fits very well in a Western tradition, I think, of the episteme versus stagnate, theory versus practice, creativity versus rationality. But this is just a narrative, this is just a structure, this is just something that this is just a rhetorics. When you go to the actual discourse, you see that this notion of the artistic is not, even by the actors who seem to be negative about it, it's not necessarily a bad thing. So for instance, in the Bacchus paper that was on the previous page, he was kind of becoming melancholic in the paper about programming now having moved to academia, where you have lost a bit of the creativity and of the inventiveness of the original programmers. Also, art in this context is not necessarily reduced to crafts. It's also about art with a big capital letter. And also, the use of art and art is also very, very present, and we kind of heard it also in the keynote talk of this morning, very present in the so-called scientific discourse, not just as a pleasantry, but also as a method for building better software. So, as I said, I cannot go too much into this, but here are Knut and Dijkstra, who are, at least in the history of computing, classically put on the stage of those who kind of defended computing as a mathematical science. But of course, as most of you know, Knut has worked a lot on literate programming, where if you read the paper on literate programming, he literally says that better documentation of programs can best be achieved by considering programs to be works of literature. But also Dijkstra, who is very famous for kind of having opposed the craftsmanship. If you kind of engage more deeply with his discourse, he has a lot of reference to craftsmanship and to art, to elegance, to beauty. So this quote here is from, so I quoted the previous quote I had, where he's very negative about the craftsmanship. This is from exactly the same text at the end, where he's actually in praise of the craftsmanship and the artistry of the programmer. What's my point here? I think that, sorry to be so quick, but I think that these kind of narratives, if you are not careful with them, I think they can be productive, but if you are not careful with them, they reduce words and fit history to a purpose, as I kind of already said at the start. There's also a risk of blind spots and misinterpretations, especially for the historians. So for instance, in history of computing, I believe that the 1950s are systematically underestimated because we have this kind of negative way of looking at it. It was just, a bit of hacking. There was no systematicity to it, so it's not that interesting. So I think it's also one of the reasons why we are still missing a proper history of computer science. And then finally, by stating these kind of oppositions, you kind of contribute to the creation of gaps that run throughout the whole field. So I was referring to, do you know Gauguin? Does anybody here know Gauguin? So Gauguin has this text, The Dry and the Wet, in which he considers 4 different cultures in computing. And so the hackers are part of that, and the dry ones are the formalists, and the wet ones are today you would say it's the agile people, and then you also have the theorists, which is the theoretical computer scientists. So that was the first insight. So be careful with words, be aware of their history and their semantic content. So the second case is about how not just computing people, but in general, even philosophers and even historians, actually, we have this tendency to fit our past to current assumptions. So here are 2 assumptions that not everybody necessarily makes, but they seem to be quite common. So the first one is theory is the captain and application is the soldier. The other one is programs are always coded. You need code for programs. To kind of undermine these 2 assumptions or kind of show that this is not always necessarily the case, I would like to go back to one of the first computing machines, ENIAC. So ENIAC is a very, very special machine, and so because it was one of the first computers, but also because the notion of program and programs as we use it today is really from that machine, from the practice around that machine. So it was a huge thing. It filled the room, but the terminology, the machine terminology, was full of programming terminology. So you had, for instance, programming cables. You had a master programmer, you had program input. So everything in the machine referred to programs, and this is where we got our notion of program from. So it's quite a quite interesting machine also, I think, for that reason. So ENIAC was publicly presented in 1946. A lot of different problems were set up on the ENIAC, and also very important, it had 2 lives. So in its first life, from 64 to 47, it was a highly modular and parallel machine with external programming. At that time, Jean Bartik talked about ENIAC as a son of a bitch to program, and I did reconstructions, and it's really because you are doing everything manually, and you also need to synchronize everything, which is really very difficult. Then it was rewired, amongst others, because of this issue. This was done by, amongst others, von Neumann, and so they turned ENIAC into a serial start program computer. So for that second life, I recommend to have a look at a book by Thomas Hake and Mark Priestley that came out in 2016. So let me go back to my text. So ENIAC, of course, did not come out of the blue. It fits into a historical development. It is from a certain perspective, you can call it an endpoint of a historical accumulation of 3 basic features, which were steadily turned into a technology because of the increasing demands for fast, correct, and precise communications. Of course, the war had played an important role in that. So the first such feature is discreteness, because discreteness gives you much higher accuracy compared to the continuous devices. Continuous is basically analog machines like the differential analyzer, but I prefer to use the term continuous in this context. So this was, of course, not new in the ENIAC context. You already had the Mark I, you had the Bell Lab machines, you had Stibitz machine. The second layer, the second advancement was the addition of conditional branching, and so the possibility of general purposeness. So this allowed for a further automation of the computational process because of the conditional, because now the machine could decide for itself what to do next. But this was also already used in some mechanical devices. So I know that in the Mark I, it's used in quite a primitive manner, but in the Bell Lab machines, it seems to have been used quite advanced and really in the general purpose way. Also, this whole idea of general purpose is very much embedded in a historical context. So for instance, the differential analyzer in that context, people were already talking about not general purpose. No, by the way, in ENIAC also nobody talks about general purpose at the time. So, but also the differential analyzer, they were thinking of a machine which could compute every differential equation. So the idea was already there to build a machine that can do more than just one thing. So these first 2 properties were already there. What's new in ENIAC is the high speed. It was absent, obviously, in the mechanical machines, and I think this is the most essential feature which made ENIAC stand out, and why it had such a huge impact on the people who worked around the machine, amongst others, von Neumann, of course. So I want to have a look at time because I fear I'm talking too slowly. So, so yeah, I will fit this. So this was just to show you how the original ENIAC. So this was not a real reconstruction, but a graphical reconstruction, if you want. So this was a number theoretical problem posed by the Lemers, Derek Lemer and his wife Emma. This is the notation Hartree introduced, which basically used the master programmer of the machine, and then here you can see part of the wiring. It's already an abstraction, of course. So this was so it relied on a prime ZIF, and so this is the you don't have much with this, but this I definitely wanted to mention this one. So this was our reconstruction of one of the conditionals on ENIAC, and so as you can see, the basic thing happens here. So you had the numerical circuits here, and the programming circuits were below, and basically what you had to do to have a conditional was to connect the numerical circuits with the programming circuit through a special adapter. If you want more details, I can explain you later. So this speed up was not a trivial thing. It had a huge epistemological impact because of the gap it created between human time and machine time. And this had consequences, epistemological consequences, but also technological consequences, if you want. So the first one concerns unpredictability and a lack of control. I think this is nicely captured in this quote by Alt, who was also involved with ENIAC. We are mentally not capable of seeing through the tremendous complications all the consequences of a computer program. So this was really new. With the mechanical computation, with the human computation, everything remained quite surveyable. With a high speed, you just could not know what was going to happen. So this was very basic as an experience. The second thing is that because of the high speed, they had to rethink computational methods. So for instance, what you typically see in programs that were set up on the machine was that they wanted to develop programs which didn't have to rely on too much input, which didn't have to rely on too much intermediate storage, because memory was mechanical. Not the whole memory, but much of the memory, especially the intermediate, was mechanical. So you had to rethink the programs, basically, or the algorithms, if you want to call them like that. Secondly, and this is the one I like most, in a certain, for me at least, that was an insight at the time, is that the stored program, in this context, this is where it happens, basically, the stored program, is a corollary of the practice and of the speed of the machine. As von Neumann himself said, it is evident that in order to be efficient, you will have to treat the problem of logical instructions on the same level on which you treat other memory problems. So, you know, with the mechanical car, so you want to kind of avoid that. And he also thought a lot about electronic memory, von Neumann. So this was kind of obvious. It had nothing to do with some kind of great theoretical insight related to a universal Turing machine. It was totally disconnected from that. So this resulted, even though it was a kind of trivial consequence, it of course had a huge impact on what happened afterwards. So the ENIAC was then rewired, and then the Ervec report was written, and then so you get the von Neumann architecture, and so the rest is history, as we say. So a third, another consequence I wanted to mention here, and which is related to the first thing I already said about the unpredictability and the lack of control. I think it is because of the high speed that we need, that people realized very soon that you needed a symbolic layer, that you needed what I call here programmed programming. And again, sorry to quote von Neumann, but it's such a kind of clear quote, I couldn't explain it any better. So, and this is also where logic comes in. Logic does not come in with the stored program, logic comes in with the programming, at least in this case, and also with others. So contemplate the prospect of locking 20 people for 2 years during which they would be steadily performing computations. And you must give them such explicit instructions at the time of incarceration that at the end of 2 years you could return and obtain the correct results for your lengthy problem. This dramatizes the necessity for high planning, foresight, and consideration of the logical nature of computation. This integration of logic in the problem is a consequence of the high speed. So, and this is, I'm not going to explain this, but it's, so so it was not only von Neumann who was thinking about programming, there were other people around ENIAC, and this is the von Neumann method, the flow diagrams, which is quite primitive when you compare it to that one, and this is by Haskell Curry, which you probably all know. He also worked with ENIAC, and he actually, based on his experiences with ENIAC, he developed what he called a theory of composition. And it is really very, very advanced for that time, but it was completely forgotten, I don't know, for several reasons, probably because the time was not ready for it, and also because he left computation and went back to logic. So where is the captain in all this? So I hope I have somehow convinced you that theoretical insights from the 1930s were not needed to develop the modern computer, nor the stored program idea. So why then do we do this kind of retrofitting of history? I think that there are at least 2 reasons. Initially, I think it was about an honest concern of trying to have what I call a rapprochement. I borrowed the term from Hao Wang, a rapprochement between theory and practice. So in the 1950s, you see both engineers, logicians, mathematicians, people working together because they really want to advance this field and they really want to work together. So it's very honest in a certain sense. But then later, basically when computer science starts to become a discipline, The theory becomes more and more of the captain because, of course, sociologically wise, it is good for your disciplinary identity that you can claim the seriousness because you have logical foundations. So this is definitely also part of that. I'm not saying it's the only reason, but it's definitely part of it. So, and then finally, as a general conclusion from this case, being theory grounded is not necessarily the right and only way. Theory need not always be the captain. So, and I think this is a general thing in Western thinking, right? That we always assume that we first need theory and then application. So I tend to disagree with that. So then my third kind of insight has to do with the disciplinary, the field's struggle for a disciplinary identity. This is, of course, not surprising, since it simply did not exist before the rise of the first computing machinery and the establishment of specific departments at the universities. And to look at this problem, I very much recommend you to have a look at a book by Matti Tedri, maybe you already know it. Computing as a Science, The Shaping of a Discipline, something like that. So it's a very nice and accessible book. So it seems that, so there it is, Science of Computing, The Shaping of a Discipline. So it seems that even today, so if you go through the discussions about if you go through these disciplinary discussions, you soon find out that there is no consensus whatsoever. And it seems that even today there are a lot of different understandings of what computer science is. We don't even agree on the name. Some call themselves software engineers, others say they are doing informatica, others say they are doing computer science, so it really depends on a lot of aspects. So these are a couple of quotes of definitions that have been around. So computer science is about information structures, computing is a natural science, computer science is about algorithms, computer science is about studying phenomena related to computers, very famous. Computer science this is one I like, is an anarchist discipline. Computer science is about complexity. Computer science is a bit of everything, like it's interdisciplinary, it's a scientific discipline, mathematical, technological. So this is like a very easy selection. There are much more definitions around. I already mentioned this problem of the naming, so I wanted to mention this little anecdote, which is kind of telling, even though it's very old and perhaps not so relevant anymore. So at some point, the editors of DataLink sent a letter to the editor of communications of the ACM, and they say, it would help our profession to be widely recognized if it had a brief, definitive, and distinctive name. This should be general enough to cover a variety of subfields, but specific enough to imply that computing applications are involved. Consider the solid professional sound of such terms as petroleum engineer or nuclear physicist. What can we use that will be equally clear-cut and at least half as impressive? The reply was, several names have been suggested, Turing engineer, Turingologist, so Turing was already there very much in late 50s, flowchartsman, applied mathematician, and applied epistemologist. So this is old stuff, I know, but it's kind of telling. So the name of the field can change the understanding of even by, so I mentioned the extra shift because, as you probably know, late 60s he was like a big enthusiast of software engineering, and then later he came to call it the doomed discipline. So it really like how you understand the field and how you kind of identify yourself within the field can even change like in your lifetime. So finally, and this is like I was very glad to hear the keynote of this morning, there's also the issue of education, what should be taught. So also this has a clear history. I have not worked a lot on this, so I'm not going to go too much into it also because I'm running out of time, but I think it's quite clear that there are historical and geographical fluctuations up to today. And so, you know, I refer here to the recent debates on computer science education for school children because there's no general agreement. And also this has a history. So for instance, if you look at Russia, they have a very, like in the late 70s, late 70s, Uspensky writes his book on post-machine, where he kind of develops an idea of how we should teach school children computer science, and this is really like the scientific approach, whereas in the US, you have developments in Logo, which is much more oriented towards coding, programming. So even so, geographically, and there are a lot of differences. So why should we care about this? So now I want to go back to my text. Is this not just another academic and hence irrelevant discussion? I think not. I think it goes to the heart of a basic problem of the field, which goes back at least to a NATO conference in not 68, but 1969. So in 1968, we have the very famous Garmisch conference in which we defined the field of software engineering and in which the crisis was also declared immediately. But there was a follow-up conference in 1969, and there the editors of the proceedings basically explaining in the introduction that the basic problem that came up there was not the crisis, it was the problem of communication gaps. So the sense of urgency in the face of common problems was not so apparent as at Garmisch. Instead, a lack of communication between different sections of the participants became a dominant feature. Just as the realization of the full magnitude of the software crisis was the main outcome of Garmisch, it seems that the realization of the significance and extent of the communication gap is the most important outcome of the Rome conference. So I think the discussions around the identity of the field, well looked at from this perspective, gains another meaning. It is about a continued set of gaps between different communities with different methods and views on what computers are or should be. But rather than contributing to that debate myself, I would rather put on the meta-historical hat and ask what is a discipline historically. As it turns out, our modern notion of discipline originates in the 19th century, and so we must there ask, in how far is a 19th century idea still suitable for a field that did not even exist yet? In other words, rather than continuing the disciplinary struggles, perhaps we should just drop the whole notion of disciplinarity itself. So this was it for the historical insights. I have a brief recap from history, but I'm going to skip it, sorry, because I'm running out of time. And so I propose we now move on to philosophy. The philosophy part will be much shorter, so luckily, because otherwise I wouldn't make it to the end of the talk. So as I announced at the start, with the historical insights and the cases, based on them, I wanted to derive a kind of philosophical framework, which is very much about what Gaston Bachelard called epistemological obstacles. So I don't have much time to really explain what they are, but I think the term, it's quite self-explanatory. I'm completely confused by it's quite self-explanatory what it says. So basically, this is the idea that current knowledge is always very much determined by a set of obstacles which we need to overcome if we want to make a change, basically. So I'm not going through the quotes, I'm sorry. So what I would like to do now is consider 3 different obstacles, or what you could consider as obstacles, I think. So the first one, ironically, is history itself, which I only mentioned very briefly here. It goes back to an insight by the media theorist Marshall McLuhan. And so he has this booklet, The Medium is a Massage, which he co-authored with an artist, basically. And so the picture you see, it's a car, and in the rear view mirror, you see a couch. And so the quote, that's which you cannot read it, sorry. So the past went that way when faced with a totally new situation. We tend always to attach ourselves to the objects, to the flavor of the most recent past. We look at the present through a rear view mirror, we march backwards into the future. So the idea is basically that humans have a tendency to stick to the old ways, especially when confronting with something radically new. And I think it is fair to say that computational technology is something quite new. So I had another slide which was basically a Dijkstra slide in his quite subversive text on the computer science education. He kind of claims programs as a radical novelty, and he explains how we should be careful in using the terminology, and that we should try and take distance from existing terms and concepts and develop new concepts. So the second obstacle concerns opacity and the alienation that follows from it. So this relates to the fact that programs themselves are historical, so they are built layer upon layer. And since each layer is built in another time, they too bear a history, and so also a set of different cultures, ideologies, methods, and practices. It is this very historicity which results in problems of opacity. It is opacity which makes that the program's historicity is hidden and ultimately ignored. This opacity goes hand in hand with the process of alienation. It turns the user, average and professional, into an ignorant user. It is this process, paraphrasing Simondon, which alienates us from this basic technique we call program. Overcoming that obstacle means to try and see through the opacity and the historical strategies that have contributed to it. This can be done, I believe, through historical research, but also by creating programs that are as open and transparent as possible. So now I go to the third obstacle, which we called dichotomies. So this concerns the Western tendency, which I already referred to a bit, to think in dichotomies. Indeed, our cultural history is full of such dichotomies, and I think they also apply to programming. So I name a few there. So concrete versus abstract, human versus machine, informal versus formal, art versus science, bottom-up versus top-down, industry versus academia, modern versus postmodern. So I propose that we abstract from these oppositions and that we model is not the right term here, that we model them in this, what I call a triangle of oppositions with three parts: society, technology, science. So such dichotomies need not be a problem per se, and they can be productive, but not in the case if they are used reductively for concepts which should not be for, or technologies which should not be forced into any side of a dichotomy. This is certainly true, I think, of programs, which I would like to describe here as an undecided, referring to a text by Jacques Derrida on the pharmacon, where he talks about writing as a pharmacon. So pharmacon can have two meanings. It can be a poison and it can be a cure. And so I will just quote it. I don't know how understandable this is for you, but I had to read it a couple of times, but I think this works very well, at least for this kind of dichotomy obstacle. So, and if one got to thinking that something like programming, far from being governed by these oppositions, opens up their very possibility without letting itself be comprehended by them, if one got to thinking that programming cannot be subsumed under concepts whose contour it draws, leaves us only its ghosts to a logic that can only seek to govern it insofar as logic arises from it, one would then have to bend into strange contortions, what could no longer even simply be called logic or discourse. One must accept the fact that here, for once, to leave a ghost behind will, in a sense, be to salvage nothing. So that's all I want to say about Derrida here. So if then we see programs as an undecided, so if you want to follow me there, this kind of reductive thinking, program as something scientific, program as a social object, program as a technology, creates a basic number of gaps, not just communication gaps, but also ideological gaps, methodological gaps, etc. Since one community will see programs in this way and another will see it in another way. This results in a disconnected set of insights into what a program is or should be without there being a shared set of methods and values. Moreover, we end up with a separation of concerns where perhaps there shouldn't be one. This process ultimately reduces the main environments in which programs are made, studied, sold, and used. So what do I mean with that? So I have this is not like generally the case, but this is one reduction I at least have encountered a couple of times. Society becomes a user with a capital letter to indicate it's not supposed to be literate. Technology is commerce, basically. Yes. I'm ready. And science becomes technology's servant. For the latter part, I would strongly recommend you to have a look at a paper by Forman from 2007, the historian of technology. So I think I'm almost there. So this is the proposal. I will not discuss this in depth. So based on all of this, my proposal would be to, and not only of me, to be a bit more anti and undisciplining about programs. Rather than to main stock to our most favored communities, journals, conferences, methods, tools, languages, I think what we might need instead is to step out of our comfort. I used this picture by Baron von Munchausen, who has to pull himself out of the I forgot the name of the English term, the swamp. So I think this is something which can be extremely challenging. I am trying to do this now in the framework of the project I mentioned, but I think and it takes a lot of effort and time, but I really believe, even though I cannot show you a product yet, that it can be very productive. And so I think that history and philosophy, understood in a general and undisciplined way, can help, but not necessarily so. So clearly, I have not given you an answer to the question, what is a computer program? But that was, of course, not the point to start with. The point is very much Heideggerian, if you want. If I got something from Heidegger, it's mostly this. It's about the significance of questions. The closer we come to the danger, the more brightly do the ways into the saving power begin to shine, and the more questioning we become, for questioning is the piety of thought. So thank you.
That's fair. So, also when you say the question, can you repeat it? Because there's no mic. Okay.
Under ENIAC, you have stated the machine now can decide what to do next.
Yes.
The machine can decide. Is this really your point of view? Can a machine decide?
Well, I should have been more careful with the anthropomorphization, but with the conditional, you have an automation of a decision process, namely either you do this or you do that, and the technology allows for this decision to be automated. That's a more careful formulation of that statement.
Because what I ask in many minds, especially in the direction of AI, is the wording "the machine decides."
Yes, but it's used quite differently, right? It's even though in that context, I mentioned this where Fabio Fossa, he's doing the semantical research on robotics and AI, and he's looking at how words which are typically associated with humans, like creativity, how they have kind of semantically shifted to the AI discourse, and what the implications of that are. So you might be interested in that.
Okay, we can do one more, but then that's it. Do one. Okay.
Yes.
You mentioned Heidegger a lot. Do you feel like Heidegger had a very significant sort of effect on your own research? And if so, why?
Yeah, so that's a hard question. So because I didn't mention a lot of philosophy like for many years, so I decided to do this again and be explicit about it. So yes, of course. I mean, I read Heidegger as a philosophy student, and he basically changed me from somebody who really was extremely frustrated. I really didn't like computers. I didn't understand them. I was frustrated with them, and he basically changed my research interests. I became, a historian of computing. So yes, of course, he has fundamentally affected my life, basically, at least professionally. Well. So yeah, but yeah, if that's what your question was.
Sadly, we don't have any more time, but thank you so much.
Thank you.